Okay, so there is a question that came in TIFR examination which goes something like this. In a laboratory frame of reference, two observers, A and B, and those observers can be spaceships, are moving along the sides of an equilateral triangle with equal speeds of c by 2. What is the speed of B with respect to A? What is the speed of B as measured by A? So this is a question on relativistic velocity transformations. Essentially, there are two objects, two observers or two spaceships that are moving at very high speeds, half the speed of light, but they are moving at a particular angle. So their paths are along the sides of an equilateral triangle. So B is moving upwards on this side of the equilateral triangle and A is moving downwards on this side of the equilateral triangle. So how to approach a question like this? So to approach a question like this, we can use the general form of the relativistic velocity expression, which includes the angles that two objects make, or we can also try to do it using the standard expressions which are derived for speeds along the x-axis, but with a certain amount of twist. The twist is that we can look at the components of velocities along x, y or z axis and then find the final speed from those components. Okay, so the question is very simple, and the way to approach it is using the relativistic velocity transformation equations, which goes something like this. So the standard formula for the velocity transformations are derived for a very simple scenario where there is an observer in the s dash frame of reference which is traveling with a certain relative velocity of v with respect to another observer in the s frame of reference. And this relative velocity is only in the direction of x or x dash axis. For that kind of a scenario, if both these two observers are looking at the velocities of some object, then that object will have velocity components ux, uy, uz with respect to the first observer, but ux dash, uy dash and uz dash with respect to the second observer. Now, how do these quantities relate to one another? Well, those are the equations that I was talking about. So ux dash is simply equal to ux minus v upon 1 minus ux v upon c square, while uy dash is equal to uy root over 1 minus v square upon c square upon 1 minus ux v upon c square. The uz dash also has a similar formula like the uy dash one. So this is the standard expression for relativistic velocity transformations, where the relative velocity is only along one particular axis, which is the x-axis. Now I can apply this similar formula in our problem if we look at the components of the velocities of B and A with respect to some defined frame of reference, and from the components we can calculate the final magnitude of the velocity by using those components. Okay, so let me define two frames of reference in this scenario here. Okay, so I have created this scenario in which there are two frames of reference, this blue one and this orange one, and it looks like that they are tilted with respect to the board, and the reason I have tilted them is because for my own convenience, so that my calculations become slightly simpler. So let me define what they are. So this is the XY frame of reference, which is essentially the board frame of reference or the laboratory frame of reference with respect to which both these objects are moving at velocity c by 2, okay, or speed c by 2. And this is the frame of reference which is x dash, y dash axis, which is associated with A. Okay, so let's suppose this frame of reference is associated with the laboratory frame of reference or the ground frame of reference, and this frame of reference is associated with A. All right, and such that the x-axis, x dash axis and this side of the triangle are all parallel to each other. Now, how does that create a convenient scenario for me? It creates a convenient scenario because now the S dash frame of reference is moving relative to the S frame of reference only along one particular axis, which is along the x-axis, right? And with a speed of v is equal to c by 2. So what I'm going to do is I'm going to define the velocity components of B with respect to this frame of reference. All right, and we don't necessarily need a z-axis because it seems from the diagram that the whole motion is confined to a particular plane. All right, now let me define what are the speeds or the velocity components of B with respect to this S frame. Okay, I'm going to call this as S here. Okay, with respect to S. Okay, so what is the velocity component of B in the x-axis? I'm going to call as ux. Okay, so velocity component of B in the x-axis, well, x is parallel to this side, so I've drawn a line here. So if you draw a particular line here, from the geometrical construction of the setup, you can see that this particular angle and this particular angle are same. It's an equilateral triangle, so all the inner angles are 60 degrees each, right? So these two lines are parallel. So this angle is equal to this angle, which is 60 degrees. All right. So if this is 60 degrees, then what is ux? So, or what is the velocity or speed of B in the x-axis? Well, first of all, it's in the negative x-axis. So I'm going to have minus c upon 2, and the angle is 60 degrees. So I'm going to have cos 60 degrees. So this is going to give me minus c upon 4. All right, so this is ux. Similarly, what is uy? So uy is simply equal to the component of speed of B along the y-axis. So what is this? So this is nothing but c upon 2 sine 60 degrees. If you look at the geometrical construction, it's sine 60 degrees. So sine 60 degrees gives us root 3 c upon 4. That's it. These are the components of speeds of B with respect to laboratory along this, the way I have defined the x and y axis. So now, what is the speed of S dash frame with respect to the S frame? V, all right, which is given by V is equal to c upon 2. That is the speed along the x axis. And S dash frame is in fact A, okay? S dash frame is in fact A. So now, I want to find out what is the speed of B with respect to S dash. Okay, so let us first look at, the velocity components of B with respect to S dash. S dash is in fact the observer A. So let's suppose we are going to have ux dash, which is what we don't know. We are going to have uy dash, which is what we don't know, and we can figure it out from these standard expressions. So if I'm going to apply these standard expressions, I'm going to get the results. So let's do that. So ux dash is equal to ux minus v upon 1 minus ux v upon c square. So I'm going to plug the values from here into this expression, and I'm going to get the answer for ux dash, which is minus c upon 4 minus v is c upon 2, and this gives me in the denominator 1 minus c upon 4 into c upon 2 upon 1 by c square. So this gives me in the numerator I have upon 4 minus c minus twice c, so minus 3c, and in the denominator the c square and these two c's gets cancelled, and I'm going to get 1 plus 1 upon 8. So this gives me an answer of minus 3c upon 4 multiplied by 8 plus 1, 9 upon 8. So this is 2, this is 3. So this gives me minus 2c upon 3. So the x dash component of the speed of B with respect to the A observer is this much. All right. Similarly, if I'm interested in uy dash, so this is going to give me from this particular expression I have uy root over 1 minus v square upon c square divided by 1 minus ux v upon c square. So this is going to become, so ui is nothing but root 3 upon 4c multiplied by 1 minus v square is c by 2 square upon c square, and in the denominator I have 1 minus c upon 4 into c upon 2 upon 1 upon c square. So the c square here gets cancelled, and finally I am left with, in the denominator I have 1, so there is a minus sign here, so 1 plus 1 upon 8, but in the numerator, so this gets cancelled, I have root over 3 c upon 4, and in the root over I have 1 minus 1 upon 4, so that becomes 4, and in the here I have 3. So this becomes, so this is nothing but root over 3 upon 4 c multiplied by root 3 upon 2 multiplied by 9 upon 8. So this gets cancelled and this becomes 3. This answer is c upon 3. So the velocity component of b along the y dash axis is c upon 3. So now I am only interested in the speed, the effective relative speed of b with respect to a. That can be easily calculated from these two components, right? So how do I do that? So finally, the relative speed of b with respect to a is u dash, which is nothing but the magnitude of ux dash square plus uy dash square overall, right? I hope you're following the discussion. So first of all, I calculated the velocity components of b with respect to the frame of reference associated with a. So the final relative velocity is nothing but the magnitude of those velocity components. So that's it. Let me plug these values here. So the ux dash is nothing but minus 2 c upon 3 square. Uy dash is c upon 3 square. If I plug these values, finally I'm going to get 4 upon 9c square plus c square upon 9. So this is going to be 5 upon 9c square. So the final answer is root 5 upon 3c. So the relative speed of this spaceship B with respect to another spaceship A is exactly this much when both of them are moving in the opposite sides of an equilateral triangle at speed c by 2 and c by 2 with respect to the lab or the ground. So that is it. So if next time you get a problem where you are required to find the relative velocities of two objects traveling near the speed of light, but they are not traveling in a straight line or in opposite directions, but rather they are traveling at a particular angle, you can create this kind of a or you can apply this kind of a method where you associate some kind of a frame of reference with one of the objects, and then you look at the speed of the other object with respect to the lab and with respect to that object, and then you will get the components of the velocities along various directions from the standard formulas, and then finally you can obtain the magnitude by applying this. That's it. So this is a problem that came in TIFR, but it is not that difficult if you look into it. That's it. Thank you very much. I'll see you in the next one.